Hi, in today's video we're going to be talking about alcohols, ethers, and epoxides. But first let's talk about some definitions. So there are several types of alcohols we're going to talk about. So if you have an R group bound to a hydroxyl group, so this is the name of the functional group, you have an alcohol. If that R group happens to be sp3 hybridized, we refer to that hydroxyl group as an alcohol. But if that R group is an sp2 hybridized, we have different names for that. So if it looks like this, it's an enol. So there's an alkene and an alcohol, an enol. And if it is on a ring like this, where the ring has all these double bonds, we call this an aromatic ring, we call this a phenol. So moving forward, if you have carbon atoms on both sides of the oxygen atom, we call this an ether. Normally these carbon atoms are sp3 hybridized. If you have sp3 hybridized carbon atoms on each side of an oxygen, but that happens to be in a three-membered ring, that is a special type of functional group called an epoxide. And it's important to recognize that the properties of these different compounds are dictated by hydrogen bonding and by the polarity of the carbon-oxygen bond. So carbon is electropositive as compared to oxygen. And there's also special properties of the epoxide because it has ring strain. It's very highly strained to have a small three-membered ring like that. All the bond angles are quite perturbed. So let's look at how to make some of these compounds. So we can often make these using SN2 chemistry. And if we do that, we have a nucleophile in the form of hydroxide reacting with our electrophile, in this case methyl iodide, to do an SN2 reaction and give us methanol. We can also use our we can also use methoxide, now an oxygen with a carbon on it, with the same electrophile, the same methyl iodide, to give us a dimethyl ether compound. Another thing to think about in the context of making ethers is which bond do we make first or last. So to make this tert-butyl methyl ether, we have to decide which side of this molecule do we break, or what bond do we break. So if we were to make the blue bond last, following this blue arrow, we'd have methoxide interacting with this tert-butyl halide. And if we were to make this red bond last, we'd have a T-butoxide anion interacting with a methyl group with a leaving group. And so let's evaluate each side. So we know from our previous work that this type of tert-butyl halide undergoes E2 mechanisms. It doesn't undergo SN2 chemistry. Methoxide is both a good nucleophile and a good base, and the fact it's a good base is going to be problematic for this reaction. On the other side, a T-butoxide we often think of as a non-nucleophilic base, but in this case, a methyl bound to a leaving group can only undergo SN2 chemistry, so it's quite small. So even though this is a non-nucleophilic base, normally, in this case, we can force it to undergo a nucleophilic reaction, and the only way of making this molecule is to, or at least via SN2 chemistry, is to use this side as the nucleophile and this as the leaving group. And so when we look at ethers, we call this the Williamson ether synthesis, we have to decide which side to make first, and we have to weigh the pros and cons of either a big nucleophile or a big electrophile. And as both sides get bigger and bigger, the reaction becomes harder and harder. Well, thank you for your time, and I look forward to seeing you next video.